The Memristor, a nonlinear two-terminal electrical device, establishes a relationship between electric charge and magnetic flux linkage. First conceptualized by Leon Chua in 1971, it completed a theoretical set of 4 primary electrical elements that already included the resistor, capacitor, and inductor. The Memristor belongs to a broader group called memristive systems, which consists of circuits constructed from familiar components that together exhibit unique properties characteristic of the ideal memristor. Since their theoretical proposal, several memristor-based technologies have appeared, most notably resistive random access memory, ReRAM. The theoretical framework introduced by Chua revealed a distinct symmetry among the basic circuit elements. The resistor relates current and voltage, the capacitor relates voltage and charge, and the inductor connects current and magnetic flux. Extending this reasoning, Chua established the memristor as an element connecting charge and magnetic flux. The defining attribute distinguishing memristors from traditional resistors stems from their ability to remember the history of applied current or voltage, establishing a dynamic rather than static relationship between these variables. Mathematically, the memristor is defined by a nonlinear functional relationship between magnetic flux linkage and the accumulated charge. The flux linkage itself can be understood as the time integral of voltage, while charge is the time integral of current. Unlike conventional resistors that provide a constant ratio of voltage to current, the memristor's resistance, memristance, depends on the total charge that is passed through it. Consequently, for memristors, the voltage at any instant equals the memristance function at that charge multiplied by the current at that moment. When the memristance remains unchanged over time, the device behaves similarly to a resistor. However, when memristance varies, the relationship between voltage and current becomes history-dependent, providing the element with its memory characteristic. If no current is applied and charge remains unchanged, the memristance stays constant, preserving the device's state. A corresponding concept called memductance functions as the inverse of memristance, defining the conductance as a memory-dependent characteristic with units matching those of traditional conductance. The model for power dissipation in memristors parallels that of resistors, with power being the product of the square of current and memristance. If memristance varies only slightly, memristors act similarly to fixed resistors under alternating currents. However, rapid changes in memristance result in decreased current and power usage, highlighting the device's unique behavior. Physically, memristance cannot be negative for a passive device. If negative memristance occurs at any charge, the device would supply power under those conditions, and if such behavior persisted for all charge levels, the device would act as an energy source under alternating current. Engineers and scientists frequently approach complex systems through modeling. In the case of memristive devices, earlier research often failed to identify memristive behavior, which has sparked debate about whether those systems should be acknowledged as memristive. A notable test was suggested to determine whether ideal memristors exist in reality or are purely theoretical constructs. The notion of memristive behavior is not limited to theoretical ideal components, but can also be observed in practical devices that act in similar ways. For instance, the current-voltage relationship in Josephson junctions of superconducting circuits follows a form analogous to memductance, reflecting memristive interactions. Discharge tubes and thermistors also exemplify memristive systems. Their resistance depends on variables such as the number of conduction electrons or temperature, respectively. In these cases, their dynamic evolution can be described with equations that mirror the defining memristive behavior. One telltale experimental signature of a memristive device is the presence of a pinched hysteresis loop in the voltage-current plot, particularly under alternating current excitation. Despite these advances and observations, the existence of a true ideal memristor in the physical world remains uncertain. Research activity peaked following a claim in 2008 by researchers at HP Labs, who provided evidence linking memristor behavior to thin films of titanium dioxide and, by extension, to the operation of ReRAM devices. They proposed that a memristor's resistance would remember the amount and direction of charge that had passed through, remaining stable even after power was removed. This idea of non-volatile memory attracted considerable attention, but also skepticism. Some in the scientific community questioned whether such devices really display the characteristics defined in Chua's original theory, or whether the observed phenomena fall within a more general category of variable resistance devices. Further examination revealed complications. Critics point out discrepancies between theoretical definitions and the physical behavior of experimental devices, noting, for instance, that actual ReRAM devices do not perfectly fit the mathematical Memristor framework, especially when considering issues such as ionic conduction and the effects of concentration polarization. Critics also note that genuine current or voltage-controlled memristors, if they existed, would violate fundamental thermodynamic limits, namely Landauer's principle, which sets a minimum energy requirement for irreversible state changes in information storage. If memristors changed state solely in response to current or voltage with absolute retention in power-off mode, thermal noise would eventually force random switching, resulting in loss of stored information over time. This stochastic behavior appears incompatible with the original memristor concept. In practice, transitions between resistance states and actual two-terminal, non-volatile memory devices are probabilistic, governed by the height of free energy barriers that separate different memory states. Lowering these barriers with an external bias increases the probability of switching, but switching can also occur spontaneously due to random thermal fluctuations. This stochasticity means that there is no unique connection between a device's present state and its entire voltage or current history, once uncertainty and noise are considered. Another point of contention involves the energy characteristics of memristive devices. All energy supplied to such elements should, in theory, dissipate as heat, yet transitioning between different resistance states must entail some material change. Critics have argued that simplistic models do not capture important asymmetries and nonlinearities in real memristive materials, leading to the development of more complex, physics-based approaches, which, though more accurate, present computational challenges. While some have argued for a definition that casts a wide net, encompassing devices such as RAM, phase change memory, and even certain biological structures, others maintain that experimental variable resistance systems observed thus far are not true memristors. Instead, they belong to a broader family of devices with similar, but not identical behavior. To evaluate potential memristors, tests involving voltage-current trajectories under bipolar excitation have been suggested. Satisfying certain curve criteria hints at memristive behavior, but the presence of nanobattery effects and the lack of comprehensive data across initial conditions and frequencies cast doubt on whether current memory technologies perfectly embody the memristor concept as originally conceived. In 2008, researchers at HP Labs developed a memristance model based on titanium dioxide thin films. In this representation, the resistance depends on the total electrical charge that has flowed through the device. The resistance function is determined by several factors: the high and low resistance states, the mobility of ions within the film, and the thickness of the film itself. Due to nonlinear ion movement and effects near the layer boundaries, additional mathematical corrections referred to as window functions were introduced to better match experimental performance to the theoretical model. When a current or voltage is applied to some memristors, the material undergoes noticeable changes in resistance, so these devices can be understood as electrically controlled switches. The analysis of the time and energy required to change resistance assumes a constant applied voltage. When switching from one resistance state to another, the energy invested in the process can be expressed in terms of the amount of charge changing during the event. The total energy dissipated is the applied voltage multiplied by this change in charge. Unlike conventional transistors, where the final device state is sensitive to the bias voltage, a memristor state depends solely on charge history. When the device switches across its resistance range, this creates a type of memory effect accompanied by a form of electrical hysteresis. In expanded form, memristive systems are described by a set of equations relating input and output signals, where the device's state evolves over time based on continuous functions. When the system is controlled by current, it translates current input to voltage output, while for voltage control, the transformation is reversed. The original idea of the memristor appears as a special case of these general governing equations, particularly when the state variable is directly related to total charge, and the rate of change of state matches the device current. Memristors and related systems reveal a unique electrical behavior known as a pinched hysteresis curve, a loop in a plot of voltage, versus current indicating a variable resistance dependent on the direction and history of electrical stimulation. This phenomenon underpins the operation of certain resistive memory types. At higher signal frequencies, the hysteresis loop shrinks and approaches the straight-line behavior typical of a simple resistor. Some versions produce loop shapes that cannot be captured using the traditional memristor model. Building on this concept, Leon Chua envisioned memristive networks as electrical circuits that could emulate the interconnected operation of neurons and synapses found in the brain. These networks adjust connectivity weights during a training phase, allowing the circuits to adapt as new information is presented. Such systems could operate with relatively simple hardware and lower electrical requirements, offering an alternative to more traditional neural networks, but further progress is needed to fully understand their potential. For a straightforward circuit of memristors in series with voltage sources, a closed-form set of equations describes the network's internal states, based on device parameters and circuit topology. Even in idealized versions with simple resistance switching, the system's evolution can be expressed through a network of interrelated differential equations, showing similarities to certain artificial neural network models, such as the Hopfield network. These properties enable memristive networks to be analyzed and designed for specific operating conditions and tasks. Because the original device models did not account for every observed material effect, researchers have expanded the memristor framework by introducing higher-order derivatives in the mathematical relationship series expansions that yield new kinds of frequency response and hysteresis behavior. Some models also include offset values to capture phenomena like the internal battery effect seen in nanostructures, which otherwise violates the predicted current voltage patterns. Various materials have been used to construct memristive devices. Titanium dioxide-based devices saw renewed attention following experiments in 2007, showing that nanoscale thin films could demonstrate charge-dependent resistance. These structures consist of thin oxide layers sandwiched between metal electrodes, with controlled oxygen vacancy concentration, giving rise to reversible changes in resistance depending on current direction. When the device's internal ions reach the physical edge of the material, further integration of current stops, and the device acts as a fixed resistance until the current direction is reversed. Other materials are found suitable for memristor behavior. Silicon dioxide thin films, long studied for their switching properties, were convincingly shown to undergo resistance changes due to the movement and creation of oxygen vacancy filaments. Polymeric materials were combined with passive ion-conducting layers to enhance memory performance for use in non-volatile memory cells. Hybrid organic-inorganic devices mimicking synapses, sometimes called synapstors, have even been employed in bio-inspired computing circuits capable of associative learning. Layered two-dimensional materials, including heterostructures of transition metal dichalcogonides, have emerged as candidates for flexible, transparent memristive devices. These can be fabricated at low cost using advanced printing methods and often display notable capacitive effects in tandem with memristive behavior, showing promise for next-generation computing inspired by biological systems. Memristors refers to memristive effects appearing in atomically thin materials and sheets, where resistance changes are observed even in single layers of certain compounds. These provide novel functional devices that feature extremely low resistance and wide resistance ranges. Their switching abilities support high-frequency applications, including next-generation telecommunications systems. Ferroelectric memristors use thin barriers of ferroelectric materials between metal electrodes. By adjusting the polarization within the ferroelectric film, the resistance can be controlled, with fine-tuning achieved by managing the intricate development of nanoscale domains. As the resistance shift results from purely electronic changes rather than atomic movement, these devices promise improved reliability. Carbon nanotubes, when arranged in specially strained bundles, have also been found to produce memristive switching. The mechanism relies on the redistribution of mechanical strain and induced electric fields, changing the conductance profile of the nanotube bundle in response to applied voltage. Biomolecular memristors leverage natural materials, such as collagen or silk fibrin, to create artificial synapses for neuromorphic applications. Current voltage characteristics in devices based on these biomaterials reflect adaptive learning behaviors. These structures are under investigation both for bioelectronic interfaces and for memory functions in broader computational systems. Within spintronic systems, memristive behavior arises from changes in the electron spin configuration. In some configurations, electron spin can transition between parallel and anti-parallel alignments separated by domain boundaries, with the associated resistance shifting as current alters the device's magnetization. Magnetic tunnel junctions use these effects, combining both intrinsic mechanisms, such as spin transfer torque, and extrinsic effects, including ion movement and redox processes, resulting in a second-order memristive response with multiple state variables. Beyond solid-state devices, newer frameworks incorporate the underlying physics of memristors to combine processing and storage in a single element, without dependence on ongoing power supply. Devices exhibiting a memory of both flux and charge can merge logic and memory operations, mimicking behaviors found in classic computing elements such as vacuum tubes or early transistors, but with a persistent state even when power is interrupted. As of now, large-scale commercial deployment of memristors has not materialized, and the devices continue to be studied primarily in research environments. Potential use cases are wide-ranging, including analog memory compatible with quantum computing systems, non-volatile solid-state memory capable of surpassing conventional flash technologies, programmable logic, analog signal processing, reconfigurable hardware, and neuromorphic systems. Within research laboratories, prototypes have demonstrated memory densities and speeds approaching or surpassing established electronic technologies, alongside reduced power consumption. Extensions of the memristor idea have spawned devices that integrate additional circuit behaviors, leading to concepts such as mem-capacitors and mem-inductors elements, whose properties also depend on their operational history. Theoretical work has generalized these further to higher-order and fractional systems, supporting richer dynamic behavior in circuits and greater modeling flexibility. On the historical side, the concept finds roots in early experiments where circuits appeared to display behavior explainable through memory-like effects, eventually formalized by Leon Chua in the early 1970s as a fourth fundamental circuit element, defined by a relationship between charge and magnetic flux. This theoretical groundwork laid the foundation for decades of developments and, with modern materials research and microfabrication, has led to a variety of demonstrations and prototype applications in advanced computing and neural network simulations. Recent advancements include demonstrations of memristor behavior operating in the harsh conditions of space and the development of commercial devices available to academic and industrial researchers. With the development of integrated memristor-based circuits, the ability to construct adaptive, memory-rich computation hardware continues to expand. Notable projects explore their role in brain-inspired computational models, incorporating learning rules inspired by biological systems, and leveraging hybrid devices capable of blurring the line between traditional memory units and processing elements for future computing architectures.